The next laboratory experiment we're going to perform in the lab is going to be the Proctor Test. So the standard and modified Proctor Test are different versions of doing practically the same thing. We're compacting soil into a known mold at various changes to the moisture content. And what that allows us to do is determine the dry unit weight at a specific moisture content, plot those values onto a curve, and determine what the crest of that curve is to then allow us to determine the maximum dry unit weight and the optimum moisture content of a specific soil. And then we use that information to compare what the compactive effort is being performed in the field at a specific job site. In order to do that, we need to understand the laboratory information to be able to calculate those values. Our learning objective is already explained. We're going to determine and then learn to perform the test methods for laboratory compaction characteristics of soil using standard effort, but I don't want to get away from the fact that modified Proctor test is also very important. They're similar. The differences, obviously, and we'll talk about them in a little bit, are the amount of effort that goes into compacting the soil. So to refresh what this is all about, you can see from the images here that there are many different opportunities and times when fill material must be placed and compacted to achieve the backfill trenches to support soil or structures, backfill trenches, lots of different situations when backfill or fill material needs to be compacted and tested. And so this just gives a few different ways, methods, and times when that takes place. You can see from the upper left and really lower left, you have a road subgrade. One's smooth and one's a little more sheep's foot. You can see in the upper left that a technician is performing a density test on the soil to compare to the laboratory results using a nuclear density gauge. There are also opportunities when backfill around pipe, backfill around manholes, other trenching activities must be performed, and backfill of that, it becomes very critical. Lower right is just an overlap gradient. It's a big cat 825, which is a large, heavy sheep's foot roller with a blade on the front. And so we'll get into looking at the specifics of compaction and why it's important, what's going on, what the concepts and background information is before we get to the actual test. So the definition of compaction is densification of soils to be more dense than what its current state is, utilizing some sort of effort or energy, which we saw in the previous picture or previous slide with many pictures in it. And what the cause or what the outcome of this is that when you densify soils, you increase the dry unit weight by rearranging particles and reducing the void space, and that reduces the air in the void space. Because the water and the soil particles are considered to be incompressible, so the only difference can be that the void space is reduced, and so the air must be escaping. Sometimes water will escape as well, especially near the surface when it can be evaporated. But the image at the bottom of the screen shows that a looser soil on the left. You can see the water is surrounding the soil particles, which is often the case. There's surface tension and surface attractions of the soil particles that attract that water. And when you have large void space, then there's air in the other spots. And when you densify it more than its loose state, then you can see that the void spaces have been reduced, but the water and the soil particles remain the same. So what we're trying to do is measure the amount of compaction that actually does occur when compactive effort is applied to a fill material or natural material when it's scarified, moisture conditioned, and recompacted. So that's the whole purpose of this, and the big picture is to allow compaction to occur to the soil to help aid in the strength, support, and or reduce the amount of erosion potential of soils. And we'll get to that as well. So As you can see here, the quality of fill is very important. When we compact the soil, we are improving the quality of that fill material that's being placed in overlap grading projects. It also improves the engineering materials to be able to support loads, create stability, reduce the potential for erosion, and it can reduce settlement. It can reduce the potential for permeability, which can be a good thing or a bad thing depending on the situation. And all of that is an outcome of reducing the void ratio. So really, that decreasing void ratio is sort of the background concept basis for leading to the rest of the items listed on this slide. Okay, so now that we understand the benefit, let's talk about how we determine that. Well, the degree of compaction really depends on lots of different things. To reduce the void ratio in soils, you really need to make sure that you understand the mechanism that goes into densification of soil. First, the amount of energy being applied is becomes very important. That's obvious. The more load and effort and energy being applied to the soil, the better compaction will be achieved. But there are other aspects to this that play a role, and that is mainly due to the amount of moisture in the soil. The correct amount of moisture will allow the contractor to achieve the compactive effort necessary on that project easier, because the water allows for lubrication and rearrangement of soil particles, especially in all soils. And the method of compaction, depending with the type of soil, will vibratory effort and energy be better than weight or load, depending on the soil type. Vibratory is usually better for looser sands. Manipulation and weight are better for clays, but also okay for sands as well. And obviously, you don't want to place too big of a lift of soil and compact the top, because then you have something called bridging that will eventually, most likely, allow for settlement or erosion in the future, which is not healthy and not really giving us the benefits of the compaction that we're looking for. You measure all of these by the reduction of the void ratio. You determine the void ratio reduction, and that is directly related to the dry unit weight of that soil. And I put a little equation at the bottom. The dry unit weight, if we recall, is the weight of the soil solids divided by the total volume. Well, if you have a reduction in your void ratio, that means your total volume has reduced. And keep in mind that the weight of the soil solids does not change. That remains constant. The soil particles are not compressible, but the void space between them is changing and can change, and that is what is ultimately changing this equation. Increase in dry unit weight means a decrease in total volume with the same amount of weight of the soil solids within that same volume. Okay, so that's really what we're looking for when we look at the degree of compaction. I mentioned water is a very important aspect to this. The soil is affected by the water practically by looking at the rearrangement due to some lubrication. And I just go through this process that with no water, the particles have difficulty rearranging and adjusting and remolding and moving around each other. So the dry unit weight is typically a little lower or much lower, depending. When you add a little bit of water, then it starts to help the particles rearrange, so the dry unit weight does increase. And with more water, or the optimum amount of water, the rearrangement is better or best, and you get the highest dry unit weight. And then you get to a point where it becomes a little too much water, and the soil begins to potentially flow, and that creates a problem, and the dry unit weight starts to decrease, because you're starting to allow the particles to flow or move around more like water, less like a more solid structure. It's important to understand that there is an optimum amount of water content to achieve the maximum amount of dry unit weight for a specific soil. And that's really the crux and key of what this whole experiment and this process is all about. This process of relative compaction is all about. Earthwork does require standards and specifications. That's the purpose of all this. This is to sort of standardize the way engineers deal with compaction and densification of soils. Geotechnical engineers often develop those specifications depending on what type of application the soils are going to have. And oftentimes you'll get, for large projects with various types of fill being placed, you will have specifications that are changing, rearranging, and moving depending on what the application is. Sometimes you'll get a road or parking lot subgrade and backfill of a foundation of a structure, and maybe backfill of trenching of pipelines, and maybe all three of those would have a different type of compaction specification for that project. Most of the time, you're looking at requiring a minimum dry unit weight. Sometimes you will also look at requiring moisture content ranges depending on how critical the moisture content is to the application. For instance, if you are looking at a clayey material being placed to prevent water flow, you would probably want to have the moisture content range be at or above optimum moisture content, and that will allow water to have less opportunity to pass through the soil. Once you have those specifications in place, then tests are performed on the fill material as it's being compacted to verify that the field unit weight is comparable or within a specific range of the laboratory dry maximum unit weight that is determined through the Proctor test, which is what we're going to talk about. So that Proctor test is a laboratory test that was developed in Los Angeles in the early 1900s, and it was specifically designed to allow for what at the time was determined to be the maximum amount of compactive effort that could be applied to that soil. Once that amount of maximum compactive effort was determined, the soil is compacted into a specific known volume mold by a specific amount of energy. The moisture content is varied to allow for a curve to be generated as the dry unit weight of the soil is changing due to the change and variation of the moisture content. The standard Proctor test, or at the time just the Proctor test, was developed to allow engineers and technicians to follow a specific standard, so everybody was speaking the same language, and we knew that the soil can be compacted at a specific rate and energy level. So the standard Proctor test is AASHTO T99 or ASTM D698. Those are basically the same exact test methods, depending on if you're utilizing them for highway projects or any other project that requires densification and field compaction. Our lab alert allows us to go through the process quickly, and then I'll show this to you in more detail in the video. We will obtain a representative sample from the site that is planned to be used for fill material, either before it's being placed or once the project begins. That material, a portion of that material, is placed into a mold at some moisture content, typically a lower moisture content. The soil is then compacted utilizing a drop weight. For the standard Proctor test listed on this, it's a 5.5 pound weight dropped at 12 inches, and it's dropped 25 times, so 25 blows for that lift. More soil is then placed, a little more than a third of the way up the mold, and the same hammer is dropped 25 times again, moving around and placing a consistent layer of energy. And then the last layer, the third layer, is placed and the compactive effort is repeated. But the third layer is important to make sure that the compacted soil layer is above the top of the mold itself. There is an extension collar that is placed on top of the mold to allow the soil to remain in the mold, but placed above the top of the mold itself. So then the next step is to trim that soil to the exact volume of the mold, so all of the soil inside the mold is compacted pretty consistently, utilizing 3 layers, and then the mold weight with the soil is obtained. Then you can subtract the weight of the mold, and you have the weight of the soil. You understand the volume of that mold, so you can determine the moist unit weight of that soil. Then a portion of that material is obtained and weighed, and a moisture content test is performed on that soil. And now you can calculate the dry unit weight based on the moist unit weight and the moisture content of that soil. Once that's completed, then the soil is typically reduced. Additional soil of the same type is obtained, and more moisture is added to it, but usually about 1.5% to 2% increase in moisture content. And then the process is repeated. In fact, the process is repeated over and over again until you at least get a complete curve to be able to obtain the maximum dry unit weight and optimum moisture content. Usually you can see a drop in weight, and on the second time the weight drops, that's typically you want 2 points over the optimum moisture content. And you know that, as we talked before, the dry unit weight will increase until the moisture content is at or above a certain level, and then it begins to decrease. And that's when you know that you have at least 2 points on the wet side of optimum. Here's a picture of the performance of the Proctor test, which also you saw in the opening slide. And these just have some equations to utilize the determination of the dry unit weight, which I've already explained, and you should know these equations very well now. Once all of those points are plotted on a curve, you can see on the right side there are 1, 2, 3, 4, 5 different points plotted in this curve. And notice there are 2 of those points that are above the crest of the curve. And once they are plotted, then that crest of the curve allows us to determine the maximum dry unit weight at the optimum moisture content. In this case, it's 19 kilograms per cubic meter at 11.8% moisture content. And it's important to understand too that you can plot the saturation level of 100%, and typically the saturation level of 80% is where the crest of the curve lies. Now that is not entirely true for all soils, but it's close. It's something that you can go by, and these are easily plotted utilizing the equation on the screen. But the point of this is the Proctor test and compaction is typically not at or above the saturation level. Usually it's slightly below saturation, and that is important because the saturated soil typically is not a good solid material to be supporting structures or roadway systems. Now it's important to mention that the modified Proctor test came about as a result of standardizing the standard Proctor test. As the compacted fill was being tested, equipment was improved, and it was noticed that the standard Proctor test was not quite, in certain soils, did not quite allow the maximum amount of energy to be applied to the soil, and many of the tests were above the 100% unit weight, which means that the maximum amount of effort was not put in, and so the most amount of dry unit weight could not be achieved with the standard Proctor test because heavy equipment got bigger, and the methods and the understanding of how to compact soil was better understood once the testing was obtained. So a modified Proctor test was determined in the 1950s. And notice that the amount of energy that is installed in the Proctor test is increased significantly. The weight of the hammer is almost doubled to 10 pounds. The drop is 50% more, or 18 inches, and the number of soil layers is increased as well to 5 instead of 3. Now the same amount of hammer blows per layer is achieved, but they're much thinner layers. If you were to calculate the amount of energy installed in the standard test versus the modified test, 1 point in the mold, you would see that is almost 4 times greater energy being applied in the modified than the standard. And so there is a modified test that can be performed too. We will do the standard test in the laboratory, but a modified test is appropriate oftentimes for silty sand materials. The standard Proctor test is oftentimes utilized for clay materials. And the reason for that is because if you were to perform the modified and the standard Proctor test on the exact same material, you would see a shift in the curve that is generated. If a standard test is often has a lower dry unit weight, which is the reason the modified Proctor test was developed, but it also has a higher optimum moisture content. So the modified has a higher dry unit weight, maximum dry unit weight, a lower optimum moisture content, and is slightly closer to the 100% saturation line, or the zero air voids line, which means you have no air in the void space of the material because it's saturated. And that's important reason for the justification of looking at sandy materials using modified Proctor and clay materials using the standard Proctor, especially when the clay material is utilized for preventing water to flow. That you would want a higher optimum moisture content if you want to prevent the water to flow. Okay. All right, so that leads us to field compaction. The amount of compaction that is achieved in the field can be calculated by this relative compaction equation. So if you understand the dry unit weight in the field, compare that to the dry unit weight determined in the laboratory, the maximum dry unit weight of the Proctor curve, multiply by 100, and you achieve the relative compaction of that soil. The standards that are developed for a project dictates the amount of relative compaction required for that site, depending on the type of backfill or fill material that's being placed. Sometimes you will also dictate the standard for the moisture content, if it's plus or minus 2% of optimum moisture content, or -1 to +3, or 0 to +4 optimum moisture content, depends on the application. And then also sometimes the amount of lift thickness that's being applied. Maybe they say 6 to 8 inch lifts maximum. That reduces the potential for bridging of that project. Here's a quick example of looking at what field compaction is occurring compared to the Proctor curve that is being plotted. So the lower left shows that an excavator is reducing or is excavating fill material. That becomes your bank. That bank has a specific dry unit weight and moisture content as it sits in place. That becomes very loose once it's excavated and being transported. But I want you to notice that the soil and the water does not change when it's being removed and transported. It does swell because there's more air because it becomes loose. And if you notice on the Proctor curve, the bank now is reduced in its dry unit weight, but the moisture content does not change. And then once compactive effort is being placed, you will notice that oftentimes the soil is being compacted, and when that is happening, the water is being exposed and sometimes evaporates, so moisture conditioning might be necessary. In this example, it looks like the water was a little higher than they wanted, so they reduced the amount of water as it's being compacted, and that allows them to achieve a higher dry unit weight, which means they're within the range or the limits of the required specifications for that project. Sometimes the bank and the loose will be on the dry side, and you will want to increase by adding water. In this particular example, the water was a little higher than optimum, but most of the time sometimes the soils can be in a drier state as well. Okay. And now when we get to the field, we can see that there are many types of tests that can be performed to measure the amount of dry unit weight and the moisture content. The first type is just this basic physical measurement of testing. So you go to the area that the fill is being compacted to. You can dig up or remove the soil itself, obtain that soil to weigh it. You can determine what the volume of the hole that you dug is, and you can do a comparison of the weight of the material that was removed to the volume of that hole, and determine the moisture unit weight, and then take a moisture content of the soil that's excavated, and then determine the dry unit weight. Compare that to the laboratory maximum dry unit weight of that specific soil. And you can do that by many methods. The sand cone method is shown in the picture on the right. A rubber balloon method is similar to the sand cone method, only it uses a balloon and water to fill up the balloon into the hole, but it's very similar to the sand because you know the unit weight of the water, so you can determine the volume of that soil or of that hole. The sand cone works in a similar fashion. You know the unit weight of the sand that fills the hole, so you can determine the volume of that hole. The drive cylinder is a little bit different, but it has the same concept. Drive a cylinder, you know how much the volume or the measurements of that cylinder are, so you can determine the moisture unit weight, take a moisture content, get the dry unit weight, compare it to the laboratory test. The second type is a wave type measurement test. It's a little more non-destructive. The nuclear density gauge utilizes radiation and the measurement of radiation as it passes through the soil. You drive a hole into the ground, put a probe down that has radiation traveling through the soil, and then it detects how much radiation is collected back into the box. And the less radiation that comes back, the more dense the soil is. That's at least for the densification portion. For the moisture portion, it has a different type of radiation that travels out of the box and then bounces off water molecules and back to a detector, and that the more that travels back, the more moisture content there. And these are calibrated, usually utilizing the physical measurements that we saw in the previous slide. There's also a new electric density test that sends radio waves between two probes, and those can be determined. The reduced radio waves, obviously, the more dense the soil is, vice versa. All these require calibration, but they're much faster than digging a hole in the ground. So now we're going to get to the video of the actual testing of the Proctor test. Okay, so you're going to receive a bulk sample like you see in the image here. That bulk sample is typically just shoveled in from the field. So it's brought in buckets, typically dried out in an oven, and then you can break apart the particles, the clumps. Then we take the material and sift it over a number 4 screen or number 4 sieve upside down, as you can see from the image. And so we only collect the material passing through the number 4. And the material we have here can be easily broken apart. You can see the rubber mallet there breaking some of it apart. You can use the hammer from the Proctor hammer that you'll see a little bit later, or you can use the rubber mallet. I'll have all of that available to you. And you want to collect enough sample that you have about 7 pounds, 7.5 pounds total of -4 material. Okay. Okay, so what you want to do is you want to collect about 5.5 pounds of material, and then you need to know the exact weight of that material, and then you add the percentage of water that you need to get the material up to about 4 or 5% below the optimum moisture content. So if you were to have, say, 3 pounds of material there, or you can do it in grams, right? If you have it in grams, you would add the appropriate amount of percentage of water by weight to this, and that's what I've done here. You can see that after I've added the right amount of water, I've mixed it. I've started to mix it with the little spade there, but then you really want to use your hands because the consistency of the moisture is really key here. You do not want dry material in the corners or anything. You do not want wet material clumps. You want to have all the material with an even distribution of moisture throughout the entire sample. All right. And you can see that the easiest way to do that is to really just get your hands dirty, get in there and mix up the material very well. Most of the time this material here will be oven dried, which means it'll only have about 1% or 1.5% of moisture in it. So I would recommend starting with a dry material, adding about 6% moisture, 6.5% moisture to start, and then you add 2% on top of that for each point beyond. I'm probably saying that there, but you can't hear me because my voice is different than what's saying there. All right, so once you have that thoroughly mixed, you can see that we have a pan. We have a mold with the extension collar installed. We have a knife and or some sort of scarifier, and we have the standard Proctor hammer there, and we have a scoop of material. So you want to take remember, you want to go at least to close to about 40% of the height for your first lift. That's about 1.5 to 2 scoops. And you can see that there is very loose. And what I like to do is I like to pack it down just a little bit with my hand before I get started. But I want to step on that mold so it doesn't go anywhere, and I want you to notice that the hammer has a collar around it, and make sure that it is clean every time you begin. And you extend that up, push the collar down onto the material, and let it drop by its own weight. Okay, then lift it up, move it around just a little bit more, and let it drop. Lift it up, move it around a little bit more, and let it drop. Obviously, you're counting the amount of blows, not letting the material get stuck in the collar. And you do this around in a circle 25 times, making sure that the mold does not move anywhere. And that's why I keep my feet on it. Okay, so after 25 blows, it should be evenly distributed all the way throughout the top of that layer. And that layer should be about 1/3 to a little bit more than 1/3 of the height from the bottom up. So after 25 blows, I clean the bottom of the hammer. I scrape or scarify the top of that layer just to make sure that the next layer has a good connection with the bottom layer there. And again, I've got about 2 scoops or so. Looks like I'm going a little bit, yeah, so right about 2 scoops total. And I pack it down just a tad with my hand. And you can see it's probably about a half an inch, 3/4 of an inch below the top of the mold or the bottom of the collar. But once it gets compacted, it'll be about 2/3 full. So then go through again, same concept. Don't let the material pack up into the extension collar for the hammer, and go around in a circle to where it's evenly distributed 25 times. I need to shine my shoes. Those look terrible. Okay. Again, the same thing. It's about 2/3 to the bottom. Scarify the top again with the knife. And then you want to get a good representative sample from your moisture conditioned sample there to finish up the top of the mold, or the top layer, or the third layer of your standard proctor. So this is going to take, those were 2 half scoops, so we're going to need a little bit more than that, obviously, because this will compact down, and we want to make sure that this last layer, once compacted, is above the top of the mold, or above the bottom of the extension collar that's there. Okay, so you usually pack it down with your fingers a little bit to be about an inch, 3/4 of an inch to an inch below the top of the extension collar. If this layer is compacted completely and it is found that it is below the top of the mold, you have to restart the entire test. So you have to take it all out of the mold, break it back down to the number 4 screen, and start over again. So again, this top layer, 25 blows, go around in a circle to where the energy is evenly distributed. If you find that it looks like it's going to be below that extension collar, before you finish, you can go ahead and stop, making sure you count the number of blows, or remember the number of blows you were on, and add more material, and then just go to 25 blows. Okay. So now once you're done, you want to remove the extension collar and remove it very slowly to where the top of the soil does not come out. You can see that we're about a half an inch or so above the top of the mold. That's perfect. That's exactly where we want to be. We don't want it to be below that. If it's below that, we have to start over. Then we take our straight edge. Straight edge has a beveled piece to it. You want to be the opposite end of that beveled piece I'm showing you right there in the video. And so you want to extend it the opposite way. You'll see, and I can show you. And then you don't want to just come across all the way from front to back. You want to start kind of in the middle and scrape down to where it is exactly the height of the mold. So you can flip it around, do it again, and then you can come all the way across then and make sure that it is exactly the height of that mold. Okay, very good. All right, then you want to clean off all of the excess material that might be resting on the mold here, like that. Then I remove the mold from the base. Some people just weigh it with the base on it and get an empty weight of the mold and the base. I like to remove the mold itself and flip it upside down, making sure we're not collecting any more material. Flip it upside down and also scarify the bottom. So I like to calibrate the whole mold without the base, just like this, to make sure it's the same on both sides. And then you should clean off all the excess, and then you need to weigh the mold with the soil in it. You should have an empty weight of that mold before you started. So you can subtract the empty weight of that mold from the weight of the mold with the soil. And go ahead and collect that weight onto your data sheet in pounds. Then once that's completed, take it back over, and you can take a rubber mallet. You don't want to damage the mold in any way, but if you loosen the soil a little bit with the rubber mallet, flip it upside down, The soil should come out fairly easily. If not, you need to use a bigger hammer. No, use the same hammer, just use more effort, and it'll eventually come out. Okay, and then once that puck comes out, you need to grab a moisture sample. So I put it back together a little bit because what we want to do is get a representative sample from top to bottom of that entire soil puck. So I place it like this, and I want to get it from the middle of that layer. So I grab my moisture can, grab the material from the center of that soil sample. So I grab a little bit from the bottom, a little bit from the middle, and a little bit from the top. Okay, you don't need but about 125 to 150 grams, so you don't need to fill that whole thing up. In fact, you don't want to go much more than that because you're going to need that soil for the next point. Okay, then obviously you get a moisture, a wet weight of your moisture sample in your dish, and you need to know the empty weight of your dish. Then you begin to break apart the leftover soil. Make sure it can pass through the force screen again. Break it up real good, and then add 2% more water to this soil. Now you should be able to break all the particles up, all the clumps and lumps up to a -4 material. Once you have that, you need to get a new weight of the material that's left over so you can estimate appropriately the amount of water to add to it. But this time the water is already in, so you want to add 2% more water to that soil sample. So you might need to use your calculator and calculate what 2% is. Again, you want to add the moisture in a fashion to where the moisture doesn't go onto the pan, it goes into the soil particles, because you need to mix it and have a thorough, consistent moisture content throughout the entire sample. Again, we're mixing it to be consistent, so where there's no dry areas in the corners or wet clumps in the centers. And that's where you just get your hands dirty and go at it, which I'm not doing yet, which I should. Okay, then I start the process over again, where we start with a bottom lift, about halfway or so, and you'll notice that the soil will start to behave a little differently the more water you add. Obviously make sure your hammer is clean, but this will be a little bit different than the last point you did, and then the next one will be a little bit more wet, and then it'll behave a little bit differently. And like I said, soil behaves differently depending on how much water is in it. That's why we need to understand those behaviors.